All right, guys, we're going to take a look at the pulley drives and sprockets part of this assignment, and I'm just going to run through it again. We do have to kind of work a little oddly here just because I need to be able to write on the board and it's not showing up like I wanted to with the first time I ran this through. So this is going to be the second attempt. If you watch the first one, none of this writing showed up. This one, hopefully, we'll get that fixed. So we're looking at pulley drives and sprockets, and they're very similar. And so what they're looking at here is that with a belt and pulley system, and the same is going to be true for a sprocket and chain system. So they're really kind of going to look at these from the same perspective. Um, that when we look at a pulley drive system, if we go from a large pulley to a small pulley, which is what we're seeing here in this picture on the left, if we go from the large pulley to the small pulley, we are going to be trading, just like we did with our simple machines, is that we're trading one thing for another. So when we go from large to small, we're going to be trading torque for speed. So the smaller one will move faster. And it's the same thing we saw with the gears. Uh, just because it is smaller, every time that big one makes one rotation, that smaller one's going to have to make more than one rotation. So its rotational speed will be greater because it's a smaller pulley. But the trade-off is while it's going faster, it's going to have less torque. So if you want to increase the speed, you can do that, but you're going to do that with the understanding that your torque is going to go down. The reason we lose torque is because we are having a smaller diameter, smaller moment arm. So if we think back to simple machines, if I have a shorter lever arm, I'm going to have less moment or torque. And so that's kind of why that happens. So the smaller one, just because it is smaller, has a shorter lever arm, and so we're going to have less torque available. The alternative would go from a smaller one to a bigger one. This is probably the more common one for us to use, especially with the VEX materials, because our VEX motors are not super strong. So normally we're trying to go this route where we're going to go from a smaller input to a larger output. Now we don't have VEX belt and pulley systems, but we do have is VEX gears, but we also have VEX chain and sprockets. So if we were doing this with VEX, it'd be a chain and sprocket system, but the idea is the same. So that as we go from that smaller input to the larger output, again, the idea is that we are making a trade. We're trading one thing for the other. So that smaller input will have to turn faster than the bigger output will, which means we're going to have less speed in our output. But because it is a larger diameter, we have a larger moment arm. So if you go back and look at like how do you calculate moment or torque, you're going to get more torque because it does have a larger diameter or larger radius. And so that's the trade-off. So if you go big to small, you're giving up torque but gaining speed. If you go small to big, you're going to gain torque but lose speed. So it's going to move slower, but it's going to be more powerful, more torque. Okay. All right, so what we want to do is kind of go through and look at how this works. So we have our three equations. You notice this does not say gear ratio because we're not dealing with gears. And so if it's not gears, it's not a gear ratio. But the ratios are all the same. So it's the same equations, just we're not calling it gear ratio now because we're not dealing with gears. So we still look at diameters. We don't have teeth option for pulleys and belt systems because there aren't any teeth on there. So what we'll do instead is we'll just look at it in terms of the diameters or the angular speed or the torque. Those are three things we can kind of look at, and they're all going to be the same equations and setup that we do with the gear ratios. So none of that's changing. It's just we're not dealing with gears. So we don't have teeth and we don't have a gear ratio as a name. Okay, so here's this picture. We got to kind of remember this picture. I don't know if I'll be able to get the picture and the words, the work on the same thing. But we have this picture, and what we're seeing here is a pretty typical belt and pulley system. Normally you see stuff like this in a car. If you ever look at the serpentine belt or the accessory belt, is what sometimes it's called. In your car, when you look under the hood, you're going to see a setup something like this on most vehicles. They'll be a little different just depending on the car. But what's happening is you have one of these pulleys that's connected directly to the drive line of your car. So as your car is spinning up the motor, that's turning the cam, and that cam is going to also then be driving one of these pulleys. In this case, I think we're looking at A as being kind of the driver. then you have a belt that's going to connect that to other things. And so those other things in your car might be your air conditioning compressor, it might be your alternator, it might be your water pump, a lot of different things that need to be powered in your car, and they're going to run on off of this belt. So as the belt's turning, it's going to allow these other things to also be operated. And so that's what we're seeing here. Thing that I want to kind of point out more than anything on this particular slide or this particular picture is that when we are turning that, this is a little different than gears, because with gears, everything that was connected directly to the next thing would turn the opposite direction. With a belt and pulley system, that is not the case. Belt and pulley system is really more dependent on whether you're inside or outside of the belt. And so if we're looking at this one, when you look at the belt, there's the inside of the belt, kind of the loop that is created by the belt as it's moving around, and then there's anything on the outside. So for this particular example that they're showing us, A, C, and D, excuse me, A, C, and D, those three pulleys are all inside of the belt. The belt just being the lines around the outside of that. And if they're inside the belt, they are going to turn the same direction. So they're either going to all turn clockwise, they're all going to turn counterclockwise, but they'll all turn the same direction. The only way we can change direction with a belt and pulley system is to put something on the outside of the belt. I say that's the only way. There's actually one other way, but it's not a very common way. The other way you could do it is to actually crisscross the belt. And you might see that on some older systems where the belt is kind of loose and it's not like super tight and has a little bit of forgiveness in the way you run it. But for a car system where you're running like an actual timing belt or a serpentine belt or something like this, you won't ever see that happen. That's just not a realistic way to do it. So for most systems, the only way for us really to change direction is to put something on the outside of the belt. And that's what you see with B. So B, if we drew the belt and kind of looked at what was inside versus outside, B is going to be outside of that belt, which means that when that belt goes by and pushes on the edge of that circle, since it's on the other side of the belt, it's going to actually rotate it the opposite direction. So in this case, and I'm going to draw this up here real quick, but I don't know if I'm going to be able to get all of this on the same screen. Let me see what I can do. Make this a little bit smaller. Okay, so what I'm going to do real quickly then, I'm going to keep this here for a second, and we're going to do a little snip on here because it's the only way I can get it to all show up on one screen here. So, or get the writing to show up. All right, so what we want to do then is let's take a look at what's happening here. So they're saying A is going clockwise, so A is going clockwise. That means anything that's inside of the loop, so as this belt goes through here, the belt's going to push this one. The belt's going to push B that way around, so B is going to be going counterclockwise. And we can tell that without having to do a lot of work, just because we can see that it is on the outside of the belt. Here the belt's going this direction, which if it's going that direction, it's going to cause this one to rotate that way around. So C is going to be going clockwise. And then same thing down here. As the belt pushes this way, it's going to push the edge of this one around that way. So it's going to cause D to go around clockwise. So all the ones that are inside of the loop are going to go clockwise. Anything that's outside the loop is counterclockwise in this case. It just depends on whatever the driver's going. So if the driver's going clockwise, everything inside the loop will go clockwise. Okay, so that's what you should have for number one. Number one, you should have B is counterclockwise, C and D are clockwise. But what we're looking at is it inside the loop or outside of the loop? Okay, I'm going to close that out. And let's bring this back up a little bit. Okay. So that was the first one. Hopefully you got that written down. If not, it's a video. You can stop it and go back and write it down. All right, number two. So number two, we're going to do this from memory a little bit because I won't have the picture pulled up because it's on the previous page here. But we are looking at the diameter, and we want to figure out what's the ratios. So let me make the snip real quick, and we'll look at the ratios. So what we're looking at is the ratios between the pulley and pulley A and the other three pulleys. So pulley A is our driver. That's the one that's causing everything to move. And so that's the reason we're going to use it as the one that we compare everything against. When we did this with gears, we kind of looked at, A versus D for a simple gear train, or we did the two next to each other and each part of that simple gear train in the compound gears. For pulley systems, everything goes back to the driver because that's the one that is causing everything else to move. That's not to say you can't compare it against other ones, but that's the only one we really know well what's happening. So that's the one we're going to go back to. So for this first one, we're comparing B to A. So we're just looking at really the diameters. So if you're writing down a formula here, it's going to be like the diameter of B over the diameter of A. That's pretty much our formula, is what we're looking for. And so what is the diameter of B? Well, if we look back at B had a diameter of 3 inches. And again, I don't have the picture up here, so you'll have to kind of scroll back through the video if you don't remember that, or you can go look at your paper. Hopefully you got the paper pulled up. But B has a diameter of 3 inches. The diameter of A was 6 inches. And so again, for these, they're ratios, so the units are going to cancel, but our ratio is going to be 3 over 6, which is 1 to 2. Okay, so it's a 1 to 2 ratio. For C and A, again, we're looking at the diameter of C over the diameter of A. For that one, of course, A is not going to change. It's still going to be 6 inches. The diameter of C was 10, so 10 inches. And so this is pretty straightforward. We're just going to divide those two. Again, units are going to cancel. This is going to be 10 over 6, which is, if we reduce that down, 5 over 3. And if you wanted to write 0.5 for the first one and 1 2/3 for the second one, or 1.67 for the second one, you can do that. I'm going to leave it in fraction because I think it's going to be more useful to us later. But if you want to put it as a decimal, you can. Last one, we're looking at diameter of D over diameter of A. And so for that one, again, A is still 6 inches because it's always going to be 6 inches for this problem. D was 8 inches. And so that one, of course, the units are going to cancel again, and we're going to get 8 over 6, which is 4 over 3. Okay, so that is what you should have on that one. So 1/2, 5/3, and 4/3. We'll use those numbers here for the next problem. So you want to keep those handy. Again, hopefully you're writing all this down in your paper or wherever you're doing this. And so I'm going to get rid of this, but hopefully you will have it. All right, so anyway, that is number 2. So number 3, they're saying, okay, well, we're still talking about this system up here. There's our system we're looking at. So there's our A, B, C, and D. So there's our case. We'll take a look at that again. What they're basically telling us for number 3 is we know the torque at A is 120 foot-pounds. We want to know what is the torque going to be at each of our other 3 pulleys. And so we're going to do kind of the same thing that we just did. And I'm going to go ahead and do the snip for this one so again that you can see the writing, because for some reason the writing is not showing up otherwise. So we'll do that. Okay. So we're going to do kind of the same thing, except now we're looking for a missing piece of information. We aren't just trying to fill in a piece of information. We want to solve for something. And so what we're going to do is we're going to take what we just did. So for this case, we're going to say, okay, well, dB over dA, that was the ratio that we got from the diameters. We know that ratio should be equal to the ratios between the torques. So we know the torque at B, which is our output, over torque at A, which is our input. That's going to work. It's going to be the same ratio as the diameters. If we go back and look at your formulas, we had diameter of the output over diameter of the input equals torque of the output over the torque of the input. That should be true. So that's what we're doing here. And we're putting A and B in there, but you could put out over in if you want. But that's what we're looking for. Okay. And we happen to know dV over dA. That one we calculated before. That was 3 over 6, which was a half. So we can go ahead and put 1/2 in there. And then we're trying to solve for the output torque, torque of B. And we know what the torque at A is. It's 120 foot-pounds. And so we're just solving this equation for torque of B. And if you want to, we can probably just figure this out by looking at it. But if you aren't sure, you can do cross multiplies. We'll do 2 times torque of B equals 1 times 120 foot-pounds. And I don't really have a lot of places to write this in here because I did not do a good job of spacing my stuff out very well. But you're going to get 2 times torque of B equals 120 foot-pounds, because 1 times 120 is still 120. And then we're going to divide by 2, and we're going to get torque B is 120 divided by 2 is 60 foot-pounds. So that is our output torque. That is the torque at B. So that's our answer. Now, hopefully you can fit it in the box better than I did. I'm going to have to erase some of this so I can do the next one, but that's what you should get there. Okay. And we're doing the exact same thing for the rest of these. So for C, we're going to say, okay, well, the diameter of C over the diameter of A, and again, that's output over input. So A is our input, C is our output here, equals the torque at C over the torque at A. And we know the DC over DA, we've calculated that before, that was 5 over 3, or 10 over 6 if you want to go back to that number. But 5 over 3 is that ratio. And then we don't know torque at C, but we do know this is 120 foot-pounds. And so we're going to solve that by cross multiply. So you're going to get 3 times torque at C equals 5 times 120. And 5 times 120, we're going to get 600 foot-pounds is our unit. And we'll divide both sides by 3. And we'll get that our final answer here is going to be 600 divided by 3 is 200 foot-pounds. Okay. So far, so good. See if we can make our writing just a little bit thinner. All right, for the next one, same deal. Again, same thing's going to happen. D over D. I guess I didn't change anything. Over D of A. So we're doing diameter, ratio of diameters is equal to torque at D over torque at A. All right. And so what do we get? Well, we have our diameter ratio from the last problem was 4 over 3. And we know that the torque at D divided by torque at A, which is 120 foot-pounds. There we go. And so we're going to do the same thing, cross multiply and solve. So 3 times torque at D is going to equal 4 times 120, which is 480 foot-pounds. And then we'll divide both sides by 3. Again, we're dividing them by 3 on both sides to cancel out those 3's and leave us just our answer. So we're going to get torque at D is equal to 480 divided by 3, and that is going to be 160 foot-pounds. So that's going to be the answer to that one. So we get 160 foot-pounds of output torque at pulley D. Okay, so that is how we do that one. And I'm going to get rid of that. There we go. So I don't actually have you do any sprocket and chain problems, but they're going to be the same. Sprocket and chain is not going to be any different than belt and pulley, except for one thing, and that is that now we do have sprockets. We have teeth again. So you could use the number of teeth as a comparison. So we don't actually have to use diameter. We could use the number of teeth for that ratio. But that's the only difference. Everything else will be the same. So if we were calculating torques like we just did, you do the same thing, except maybe you'd have the number of teeth instead of the diameter. But the idea is not going to change. So those are going to be the same thing. All right, last part of this is going to be some questions. And we just want to talk about this a little bit. And I don't know, I guess I can go ahead and do a snip for this. We won't necessarily answer all these, because I do want you to think about it and kind of come up with your own answer to this. But when we're looking at these questions, first was asking about timing belts. So this one I do want to talk about a little bit, because you may or may not be familiar with what timing belts do. So we want to talk about that. That is the first question. What is the specific purpose of a timing belt? And what a timing belt is going to do in a car engine is make sure that everything is operating at the correct time. So everything that you have within that engine, you've got the cylinders moving, you've got your crankshaft turning, you've got valves opening and closing. All those things are working together to make your engine run. You need to have the valves open to let fuel in at the correct time, so that you can then move the cylinder up and compress that. Then you need your spark plug to fire at the correct time. And all these things are timed or coordinated by that timing belt. And so if that timing belt is not working correctly, if these things are not staying in proper alignment, proper timing with each other, you're going to have where spark plug's going to fire at the wrong time, or you've got you don't open the valve at the correct time to let the fuel in, or you don't open the exhaust valve at the correct time to let the exhaust gases out. And all those things are going to make your car not run well. In fact, they may not run at all, depending on how far out of alignment they are. If they're slightly out, it will probably run, but probably run a little bit rough, or maybe a lot rough. But needless to say, it's not a good thing for your engine. So the timing belt is there to keep all that running together at the correct times. And so just if you want to get an idea of what a timing belt looks like, a normal belt is going to have a flat sides on both sides, and they might have a V shape to them, but they're all basically flat. What a timing belt has is teeth on it. So it's a belt, like a rubberized belt, but one side or maybe both sides, they do have some that have teeth on both sides, but most of the time in the car, it's just going to have teeth on one side. It's going to have teeth like that, and what the teeth are doing is keeping the belt from slipping. It keeps the belt properly turning at the same rate every time, because one of the biggest problems we have with belt and pulley systems is that the belt can slip, and sometimes that's a problem, sometimes it's not, but it is something that happens pretty often. If you over tension it or under tension that belt, especially if it's under tensioned, it has a tendency to just slip, and that means that the input and output pulleys will no longer be synchronized with each other the same way. One will have moved and the other will not. And when that happens, now our timing would be off. And so to use a belt for your car would be a problem if we did not have teeth. And so they put the teeth in here to keep it from slipping and keeping it turning at the same rate always. So that way you know that it's going to keep the same relationship between when the valves are opening to when the cylinder moves to when the spark plugs fire, all that kind of stuff. Okay. Now, with that being said, timing belts are belts, but they do have the teeth on there, which is very similar to chain and sprocket, because chain and sprocket system, because you do have the teeth on the sprocket fitting into the gaps in the chain, that is how that also will keep its kind of orientation or its timing the same. So that's where it kind of acts a little bit like both. And so the second part of the question is, do you feel like it acts more like a belt and pulley system or more like a sprocket and chain system? And there's not a right or wrong answer to that. It's just kind of, you want to give your answer, but you want to justify why you believe it is. So you could say it's more like a belt and pulley just because of its construction. Maybe you're saying it's more like sprocket and chain because it keeps it from slipping. Whatever your reasoning is, it's fine. Just make sure you give some reasoning for why you think that's the way it is. But yeah, so many engines have timing belts that are made of rubberized material with those teeth on them, and the teeth are rubberized. They're like kind of like car tire kind of rubber that's that hard, strong, but still flexible. But you do find occasionally timing chains instead. And the reason you see a timing chain is that it is going to do exactly the same job. The downside of the timing chain is you have to keep it oiled, keep it lubricated. So if it gets dried out and kind of gets rusty and gets stiff and doesn't move easily, that's a problem. And you don't really run into that problem with the timing belt because belts are much more flexible and they don't need that lubrication. They don't have to be oiled. So there are some good and bad parts of both the things. The timing chain would be stronger. It's not going to break. Timing belts usually don't break. They're usually pretty strong. They most of them are steel belted kind of deal where they've got like some steel cabling running through them to kind of give them some extra strength. Otherwise, they wouldn't hold up very well. Okay, so anyway, that's kind of what they're looking for there. And again, I'll let you answer it however you want to, but I just wanted to kind of talk to you about what that was talking about. Second one is asking us about wheel and axles and how do we get more output speed by adjusting the size of your input axle. So we're saying basically I've got some kind of either a belt system or a sprocket system. It doesn't really matter which one we look at, where I have an input and an output. So I have an input and an output. And what they're saying is, I want to get more speed of the output by not adjusting the size of either one of those pulleys or sprockets. What I want to adjust is the size of the axle. Okay. And so this is going to be a little bit tougher question. I'm going to leave it to you guys to kind of think it through here. But the question basically is, what can I do to adjust the size of this axle? Do I want to make it bigger, or do I want the axle to be smaller to get more overall speed? Now, to get more output speed really means I'm going to get more input speed, because if I'm not changing the size of my axles, or it's not changing the size of my sprockets or my pulleys, whichever way I'm going with that, then the only way I can get more output speed at the output sprocket or output pulley is to increase the speed of my input pulley. So the question is, like, how can I do that? And we say speed, it's not rotational speed that we're necessarily messing with when we do the simple machine. We do want a greater output speed from a rotational sense, but realistically, what I'm going to be looking at is, how do I adjust the size of that axle so that the linear speed of my output will be greater than the input. So you're kind of coming back to this idea of force and distance. When we looked at our wheel and axle system, we said that you're trading one thing for the other, you're trading force for distance. And so if I made the axle bigger, I got to be careful not to tell you too much because I want you to figure this out a little bit. But if I make the axle bigger compared to the wheel, we want to think about what happens to my force versus my distance. Now, the distance we're talking about is really going to be speed in the sense that we're looking at, because when we say distance, how far around does it rotate? If I increase the size of my wheel compared to my axle, I am going to get more speed, linear speed. And so that's kind of what I want here. I want this to be changed in that ratio. Now, I can't change the size of my wheel, which is my sprocket. So if I want the wheel to be bigger, but I can't make the wheel bigger, what could I do to my axle to increase that difference? That's really what I want to do. So would I increase the size of the axle, or would I decrease the size of the axle? And I feel like if I tell you any more, I'm basically just going to give you the answer. I may have already done that, but think about that. That's what you want to think about. Okay. Last question here is asking about riding a bike. And again, I don't know, I'm assuming most people have ridden bikes before. And I know that's not necessarily a good assumption, but I'm going to hope it is. If you've not ridden a bike, here's what you want to know about this. If I have a multi-speed bike, a 10-speed, a 12-speed, a 20-speed, whatever, however many speeds your bike has, 15 speed, you have the ability to adjust your speed based on the gearing. And what you're doing is you're switching gears and gear ratios. And really all it is, it's a simple gear train that you're adjusting. But what's happening is, as you're going, you're switching the size of the gear. So maybe you have it here at one point, and then you've got multiple gears you can switch through on this first one. So maybe there's like 2 gears, or maybe there's 3 gears that you can switch through. I guess I say gears, they're really sprockets because it's sprocket and chain systems. So maybe you have 2 or 3 sprockets there, and then over on this one you've got 3 or 4 here as well. And so what happens is, as you're riding, you're switching gears by moving the chain from one set to the other. And it's a little complicated. They have a whole system that your bike uses to make that change, the derailleur system. But what'll happen then is you might change it. So instead of being that way, maybe you're going here. So what we want to think about is, what am I changing? And of course, I've drawn a little extra stuff on here. So let me erase this one, and we'll go back and look at this way. So if I have it this way, where this is my input and this is my output, and then I switch it to where this is my input and this is my output, what's changing from one to the other? Well, here I'm going from a big to a small, so my output is going to go faster, but I'm going to have less torque. Okay. If I go this route, I'm going to have less output speed, but I'm going to have more torque. So what's the trade-off? Well, that means I have to pedal more times here on the second one. So my input is more pedaling. I'm going to have more pedaling on that one. That's terrible. You can't hardly read that. But on that input, I'm going to have more pedaling. I have to pedal more. So every time I rotate the output one time, I'm going to have pedaled more than one time around on my input. But what I'm going to get is I'm going to get more output torque. So I'm going to be able to go a little better. And so when you're riding up a hill, if you've ever ridden a multi-speed bike, when you're going uphill, this is generally how you want to go. You're going to switch down to a gear so that you pedal more with less torque. You put less torque in, but you're going to get more output torque, but it feels like you're just pedaling a lot. You're pedaling more, multiple times around for every rotation of your wheel. So you feel like, oh man, I'm just pedaling like crazy and I'm not getting very far. That's what it's saying. It says, why does it seem like you're pedaling a lot to cover a short distance? Because you're in a situation where your input gear, your input sprocket is smaller than your output sprocket. And so you're having to turn the pedal multiple times to get one turn of your output of your wheel. And so that just feels to you like you're putting a lot of pedaling in to get a short distance. Now, why do we do that? Because it's easier. I can pedal easier that way. And so if I'm going up a hill where I need more torque to be able to push myself up that hill, if I don't have a lot of more ability to put torque in myself, I'll shift down to this lower gear where I can pedal easier. It's easier to pedal, and I'll get more output torque. So it just makes it easier for me as a bike rider to do that. So if you're going up a steep hill, this is kind of how you're going to go. And so it says, what happens if you switch to a higher gear in hopes of not having to pedal as much? Well, then you're kind of changing from here over to this side. Say, okay, well now I'm at a situation where my output may be bigger than my input, or my output might be smaller than my input. May not be. It may just be closer. They may be just getting to where these are more equal sized. But you're just switching it to where you're more of this situation. So where your input is larger in comparison to your output. So you could get all the way to this situation where the input is a larger sprocket than the output. In this case, I'm going to have more output speed, but less torque. And then on my input side, I am having to pedal less, but it's harder because I'm getting more torque on that side. So on my input side, I have to put more torque in, but I don't have to pedal as much. So I'm trading off where I don't have to pedal as much. I don't have to do as many rotations of my sprocket, but it's going to feel harder for me. I'm having to put more torque in because that end has more torque. So my output, I'm not going to get as much power out. So this is usually the setup you want whenever you're going like on a downhill or you're going on a maybe even flat surface, although maybe flat surface you don't want to go. I don't know. I'm not a bike rider, so I don't know like the best options for things. But if you're going downhill, this is probably where you're going to be. So I can pedal less, and it's easier for me to pedal because even though I have to pedal harder, if I'm going downhill, I'm not having to resist as much force, so I can do it easier. And so maybe I'll put myself in this situation where I can go fast. I want to go fast down that hill or go fast on a flat. I'll go more towards this style. Whereas if I'm going uphill, I'm going to go more towards the right one where I have the smaller input and a bigger output. So that way I can pedal more, but I'm not going to go as fast, but I am going to get more output torque. So I'm going to be able to make it up the hill. Okay. All right. So I have not answered, but I've hopefully given you a lot of help towards answering these questions. And those are the end of this assignment. So I'm going to go ahead and close this out. And then, yeah, that should be the end of that assignment. So I will end it there. Good luck, guys.